Okay, this is the second and very late showing up video for Chapter 6, Categorical Data Analysis. So this is Chisquare. This is a video on how to conceptualize and perform a Chisquare test, goodness of fit. Now there are two types of Chisquare tests. The thing they have in common is that they both use the Chisquare distribution, but they use it in different ways. They have things in common, but they're different kinds of tests. So first I'll talk about what we call a one-way chi-square or a goodness of fit test in this lecture. The next lecture I'll talk about the independence test, chi-square test for independence or test of independence, sometimes called the two-way chi-square. And there are 3 and 4 and bazillion-way chi-squares if you really feel like it, but nobody in their right mind tries to interpret those. Okay, so chi-squared is like a proportion test, but with more than 2 categories. A proportion test, you only have 2 possible categories. A single sample proportion test is what you should be thinking here. So what percentage of yeses versus nos? What percentage of males versus females? A single sample proportion test means that you're looking at one proportion, but there are 2 categories, but you don't have to talk about both categories. You don't have to test both categories, because if you know the proportion of males is 56%, then females must be 44%, etc. So when there's only 2 proportions and they account for all the possibilities, then or 2 categories when they account for all the possibilities, you can do a single sample proportion test, and you've got 2 categories, but you're only dealing with one of them because the other one is just implied. But if you have more than 2 categories, like say you have male, female, and prefer not to answer, or let's say you have yes, no, and I'm not sure, and maybe. So you have more than 2 possibilities, and you're looking at counts and the number of observations that fall into each of those categories, not a numerical value for each of those. It's not like what's the scale value for the males and the scale value for the females. No, it's just how many males, how many females, how many prefer not to answer, or how many yeses, how many nos, how many people, for instance, said yes, how many people said no, how many people said I prefer not to answer, and how many people said I don't know. So if you're looking at just numbers, then you've got what we call binned data. So think of these marbles as one observation each. I would love to make myself a little toy like this someday. And this is a little toy that drops marbles into slots. We can call those slots bins, like a garbage bin. So with binned data, we're thinking about the number of observations that fall in each bin. That's the only thing we really care about. We don't care about what the value is, because the value is just, is it in the bin or isn't it? That's all. The value is just which bin is it in. So you have several categories, and this is important. Each observation can be in one and only one category. If you have a situation, and there are many of them, where observations can be in multiple categories, or multiple categories can kind of bleed into each other, then you can't use this one-way chi-squared test. So this is a different way, as I mentioned before with proportion tests, of looking at binary data. So you could have a bunch of variables. This variable is the observation in here, yes or no, binary. And then another variable, is the observation here, yes or no, binary, 1 or 0, etc. Each variable could be, or each category could represent a variable of is the observation there, yes or no. You'll note that you only need, let's see, there's 1, 2, 3, 4, 5, 6. There are 7 categories here. You only need 6 variables to represent this, because once you've gotten up to 6, if an observation is not here, and it's 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 not here, and it has to be somewhere, then it must be here. So it's interesting, for 7 categories, you only really need 6 variables to represent that. The 7th is redundant. For 5 categories, you only need 4. And like I mentioned before, for 2 categories, you only need 1. So a research question that fits, or that can be answered by a one-way chi-square test is, does the pattern of binning, the pattern in which all these observations fall, does it fit some benchmark, hypothetical pattern? And that hypothetical pattern will be the null hypothesis. The null hypothesis will be a pattern of frequencies. So for instance, looking at a close-up of this picture from the previous slide, we might want to know how closely that pattern follows a normal distribution. So here's the actual counts. There's 1 marble here, there's 6 marbles here, there are 10 here, 15, 13, 4, and 1. The normal distribution would give us a slightly different distribution. For instance, this category probably has 1 or 2 too many marbles. That one might need 1 or 2 more. That one might have 1 extra. That one has probably 2 extra, maybe 3 extra. And that one looks okay. So it's not quite normal, but we're not quite exactly sure if that's a big deal Of course, every sample is going to be a sample. It's going to be different. So let's take another situation. Are people in a city equally likely to prefer particular stores for their home improvement needs? Let's say you interview 24 randomly selected people from a city and ask which store they prefer. And there's only 3 stores in town, small town. There's a Lowe's, there's a Home Depot, and there's an Ace Hardware. And so we find out that 6 people say they prefer Lowe's, 8 people Home Depot, 3 say Ace Hardware, and then 7 people say different store, not on the list. Maybe they go next town over and buy their lumber or their toilet plungers or whatever. So pay attention here to the fact that we had to kind of manipulate this situation so people couldn't say, I have 2 preferences. Because if you want to use chi-square, each observation can only fall in one category. So you can't put a person here and a person here because they like Lowe's and Home Depot equally. That wouldn't work for chi-square. So you have to have certain situations that work. So let's think about binning. You've got 6 people here, 8 people here, 3 people here, and 7 people here. A uniform distribution for 24 people, that's 24 people, a uniform distribution would say people should all be there. And there should be 6 in every category, right? 24 observations, 4 categories, would be 6 per category. So one null hypothesis might be that people prefer the stores equally, that there's an equal preference for the stores. If you reject that null hypothesis, then you might look and see which store is the most preferred. If the null hypothesis can't be rejected, then you say, well, what am I even looking for preferred store for? Because there's nothing that's really preferred more than anything else. So we can look at the deviations from the uniform distribution, and we can use those as an index of the extent to which our observed pattern fails to fit. In other words, it's like a badness of fit test, really, in which it fails to fit the pattern. So here, this category, there are 2, let's say, wrong observations. There are 2 patterns, or 2 observations that deviate from the null hypothesis. The null hypothesis says there should be 6 in each. And that's just because we thought, let's test and see if our pattern is different from just even Steven. And even Steven is a very common null hypothesis. It's probably not its technical name, but that's what I sometimes call it, because I watched Seinfeld a bit. And this one, there are 3 observations that should have been there if there was a uniform distribution. So this one deviates by 3. The observed deviates from the expected. The null hypothesis is the expected value. It deviates by 3. This one deviates by 1. This one deviates by 0. This is the expected value, so no deviation there. So we could add up these deviations here. Well, this is deviations. This is the same thing that we're doing in a slightly different way with count data instead of numerical data, scale data. This is the same thing that we do when we calculate a standard deviation or something like that. When we do a NOVA and t-test, it's all based on deviations from the mean. Well, here it's not deviations from the mean. It's deviations of counts, of frequencies of observations in categories from expected counts. So deviation of observed from expected. That's what we're always looking at with hypothesis tests, right? The difference between observed values and expected values under the null hypothesis. So here's another example from my research. I had people go out and interview people that they knew in the Rio Grande Valley. Students went out and did interviews, and I thought, did they get a representative sample? And I thought, maybe I can check just the ages of the interviewees, and that'll give me an idea of whether the sample was representative of the Rio Grande Valley population. So this is the frequency distribution, the bar chart of the categories of ages that my students conducted. Well, here's the predicted frequencies. This is what the frequency is with this number of participants, 250 or something. With this number of participants, this is what the bar chart should have looked like if it followed the census. You'll see that there's an awful lot of young people. They were college students. They interviewed people that were their age, right? They interviewed their friends. So later I tried to change the format, but we can see that there's big deviations. There's the deviation in that category. They interviewed way too many 18 to 21-year-olds, way too many 22 to 25-year-olds. 26 to 29-year-olds, they were dead on. They were really incredibly close, like practically dead on what the census said for 18 to 29-year-olds. But that was kind of an accident because their frequencies are dropping like this, and the census frequencies build up to a mode here of 46 to 49 and then start to drop. So these are all deviations. These are all wrongness. those wrongnesses add up a lot. So the chi-square goodness of fit test for whether my observed frequencies fit the expected frequencies according to the census values, and that would be the null hypothesis, this green line, that chi-square would almost certainly be rejected pretty hard. The null hypothesis would be rejected. This would be a significant result. So the chi-square test, the goodness of fit test, is really a badness of fit test, and sometimes the null hypothesis is even-steven, meaning equal frequencies in each category, and if you can't think of anything else, go with that one. But not always. Sometimes there are some much more reasonable things that aren't even-steven. So we set this up as just a frequency table, and I always picture it as a bar chart or a histogram. And we look at the observed frequency, the frequencies that actually occurred in our data in each category, and then we also write in that table the expected frequency. If you put it on a graph, you can see the vertical distance between observed and expected. But in numbers, you can just subtract these two, so you can get a difference between observed and expected. So sometimes the null hypothesis is equal frequencies, like I said, even-steven. And then we test the significance of the added up differences between observed and expected. So we add up the deviations, which is pretty similar to variance, right? This is how you calculate variance, x minus x bar. But it's not means this time. It's frequencies in each category, observed frequencies minus expected frequencies. The null hypothesis says the observed should be the expected frequency, and that's a pretty vague version of the null hypothesis, but that's what we're going to go with. And the alternative hypothesis says the observed values will not fit the null hypothesis expected frequency. So thinking about that null hypothesis for a one-way goodness of fit test is pretty important. So when we put this in formula form, it's like this. This looks a lot like the value, a lot like the formula for variance, except instead of x minus x bar, we have O minus E. So for each category, we just take the observed value in that category, the number of people who actually fall, or number of observations that fall in that category, and look at the difference between that and what we would expect if the null hypothesis were true. We square that difference. The reason we do that principally is to make sure that the result is positive no matter what. But squaring has other advantages. And then we divide that difference by the expected difference. So we're getting a ratio of how bad, like the percentage of badness, essentially, the percentage of not fitting. So observe the part minus, or divided by the whole. So this is a part squared divided by the whole, or divided by part of the whole. Anyway, it's an index of how bad it is. And then you add all those things up, and that makes a chi-squared value. So an F value is a ratio between two variances. A T value is kind of like a normal distribution value. And a chi-squared value is this. It's this added up squared difference between observed and expected divided by expected. All those things added up across all the different categories that you have. And then you just take that chi-squared value and you look at a table. And the table in the back of your book is going to tell you that you need to know the degrees of freedom. Well, the degrees of freedom doesn't have to do with the number of observations. It just has to do with the number of categories. So it's often a pretty small number of degrees of freedom. So the number of categories or bins that you're dealing with. And it's just the number of categories minus 1. So here's what the chi-squared distributions look like. Like the T distribution, it's actually not one distribution. It's a different one for each degrees of freedom. You don't have to know this. Just keep in mind that A, it's horribly asymmetrical. The tail always goes off to the right. It's a lot like the F distribution that way. And B, there's a different one for each degrees of freedom. So that's why you have to use this table and find critical chi-square values if you're going to do this by hand and look up with the degrees of freedom that way. So hypothesis testing with the chi-square test, it's similar to what we do before. You state the null and the alternative hypotheses. If you feel like it, you can draw a diagram of the chi-square distribution, but that gets a little confusing because it's sort of abstract. You look up the critical chi-squared value, and then you state your rejection rule, and you say, if such and such happens, then I will reject the null hypothesis. If not, then I won't. You calculate the observed chi-squared value using that formula with the sigma and the O minus E squared, etc. And then based on comparing your observed to critical, you state your decision about the null hypothesis, and you state your conclusion. What we've seen before. So here's example number 1. Let's say a programming team is trying to debug a very complex computer program. They don't want to check hundreds of lines of code, so they suspect the problem might be in one of 3 areas, each of which would be more likely to generate a particular kind of error. So they'll just run the program a bunch of times and see how frequently the errors occur, and if the errors are in this area, then they kind of know where to look for the bug, and if they're in the other area, etc. So an error in like area 1 of the code would generate a seg fault, and area 2 error would generate a stack overflow, probably most of the time, and an area 3 error would probably mostly generate pointer dereference errors. So if there's problems in area 1 of the code or area 2 or area 3 of the code, they should be able to get an idea of where they are by looking at the types of errors that are generated when they try and run the data. So the first step, if this strategy is going to be followed, is to find out if the errors are even equally distributed. If they're equally distributed, then they're wasting their time. This is not going to help them. They should try something else. They might just have to do it all by hand, one line at a time. So they run the application 100 times with varying like what gets input into it, and it generates all kinds of errors. And it generates an error every single time, and they count the kinds of errors generated. So their hypothesis, the null hypothesis, is that the 3 types of programming errors are equally likely to occur. So they can't tell which one is most common until they first look and see if they're equally common. Kind of like ANOVA. You do the F-test, the omnibus test first, and then you do individual tests. The alternative hypothesis is that the 3 types of errors are not equally probable, but there are differences in their frequencies. Now, of course, there will be differences in the sample, but they're trying to guess not, are there differences in this 100 times we ran the code, because of course there will be differences. They're saying this 100 times we run the program is only a sample of the millions and millions of times it could be run with all the different parameters and all the different values that could be fed into it in the beginning. So this is just a sample, and from the differences here we'll see if these deviate enough from even Steven essentially, that we believe that they represent something actually going on deeper in the code, and therefore it's worth our time to zoom in on whatever is the most common error. So here's their data. They've got these 3 categories. They've got a seg fault, stack overflow, and pointer dereference. Seg fault happens 25 out of 100 times, stack overflow 28, and pointer dereference 47. It looks right on the surface like pointer dereference is a lot more common than those 2, but that could just be random sampling error. They don't want to waste their time going and looking in area 3 of the code if this is likely to have happened just with a random sampling procedure. So they do the chi-square. The first thing you do with chi-square is you figure out what the null hypothesis says the frequencies should have been. This is the expected frequencies. The null hypothesis in this case is even Steven. They want to see if this deviates from all of the errors being equally likely, right? So that's an even Steven null hypothesis. So if they were equally likely, then we take 100 and divide it by the number of categories and say there should have been 33.3 errors here. Now, I know you can't have a 0.3 error, but that's okay. This is just for the math. These are discrete numbers, but we can have non-discrete numbers and treat discrete numbers very badly in the middle of the math procedure as long as it's going someplace interesting then. That makes sense. So we would expect these expected frequencies to be here and here. So taking this minus this, we get a minus 8.3 for seg fault. That's the deviation from expected. Minus 5.3, so it's 5.3 fewer than we would have expected. And this is 13.7 errors more than we would have expected if the population is that they are truly equal, or equally likely. So we square that, and then we divide it by the expected value. So you've got this squared is this, divided by 33.3 is this, if I did my math correctly. And then you add all these up, and you get 8.55. That's chi-squared. That's the chi-squared observed value. So we could graph this like this. I just threw those numbers in there. The red value is the null hypothesis. The null hypothesis says everything is even. 33.3 errors in each category. The blue bars are what actually happened. Here, here, and here. So that's a wrongness. That's a deviation. So pointer dereferences were way too common. Seg faults were not common enough, and stack overflows were not common enough. So those are the deviations. And if you just add up those yellow boxes, that's 8.55. Well, with funky math there. Conceptually, that's the same thing. You add up those deviations, and that's your chi-square. So you need to look up some values in the table in the back of your book first before you test this. You find a critical chi-square for 2 degrees of freedom. 2 degrees of freedom because there are 3 kinds of errors, in other words, 3 categories. And degrees of freedom for chi-square is the number of categories minus 1. And let's say we set alpha at 0.05, then 2 degrees of freedom, alpha 0.05. The critical chi-square is 5.99. So the chi-square that we actually observed, our observed chi-square from our data, as we saw previously, was 8.55. That's bigger than 5.99. That's all we have to worry about. There's no two-tailed, one-tailed, left, right. It's all to the right, and it's always just, is observed bigger than critical, at the end. If your chi-squared is big, it's more significant, the end. It's like F, it's very simple. So chi-squared is greater than, the observed is greater than critical, therefore P is less than 0.05. We don't know exactly what P is, and we don't care. It's less than 0.05. We reject the null hypothesis. And remember that the null hypothesis was even Steven. So our conclusion is that the errors from the program are not equally likely to occur. Therefore, the strategy that they're following, it might actually reduce their debugging time, so it's worth it. And if you're a programmer, you know some good statistics, so you probably could bust this out in about 5 minutes and save yourself several hours of trying to debug code. So the next step would be to do proportion tests between pairs of types, so between segfault and pointer dereference, and between segfault and Stack Overflow, etc., to determine which of those differences are statistically significant, so you could have a better idea of which place to look. Now, probably it's going to be the pointer dereference where you look, but there might be some extra information you could get in there as well. So just like an ANOVA, when you get a significant chi-square, in this case, in this way, sometimes the next step would be to go do individual proportion tests between all pairs of frequencies to determine which of those are statistically significant, to get a more fine-grained view of where the differences actually are. So let's take example number 2. A geneticist is breeding red and white flowers together, and she suspects that the color gene is neither dominant nor recessive, which should mean by Mendelian genetics that exactly 1/4 of the resulting flowers would be red, 1/4 of them should be white, and 1/2 pink. But I mean, that's population values. Those proportions should show up over millions and millions of flower breedings. In a small sample, it'll be slightly different. So her first crop produces 64 crossbred flowers. Do they follow the expected pattern? Because if they don't, then she's wrong about something pretty important, about whether the gene is like she says, neither dominant nor recessive. Now, the null hypothesis is that they should follow this pattern. So you see that the null hypothesis, she's actually kind of rooting for it. And this happens a lot when we get into stuff that's not t-tests and ANOVA. The null hypothesis sometimes kind of becomes your friend. You're actually hoping the null hypothesis turns out to be supported. And sometimes you set your alpha really big, like 0.10 or 0.15, to give the null hypothesis a big chance of being rejected. But we'll just leave it at 0.01 here for fun and kicks and giggles. So the null hypothesis is that will be the frequency. That will be the proportion of the flowers. And the alternative hypothesis is that there will be some different distribution. The 3 types... Ooh. Yeah, there's a problem. Hang on. Magically, we have the actual alternative hypothesis. The distribution of flower colors does not follow the pattern suggested by the null hypothesis. So the null hypothesis is that she's right. The alternative hypothesis is that she's wrong, interestingly. So here's some data. She has these 64 flowers, and the observed value, that's an O, not a 0, is that 18 of them are red, 16 are white, and 30 are pink. Is this close enough to the expected value? With 64 flowers, 1/4 of 64 is 16, so 1/4 of the flowers, 16 of them should have been red. 18 is pretty close. 16 should have been white. That's exactly right, so we know that one's good. And 32 of them should have been pink, but there were only 30 that were pink. So it's pretty close, but is it close enough? Well, we'll find out. So we look at observed minus expected, and we get our deviations. We square those deviations. We divide them by expected. Our chi-square value, as if we add up all those individual chi-square components, is 0.38. So here's how we could have graphed that data. The red bars are the expected values, so we have red flowers should have been here, but they were here. White flowers should have been here, and they exactly were. And pink flowers should have been here, but they're actually slightly less frequent than that, less common than that. So there are the deviations. There's no deviation there, so I tried to have like just a straight bar, and then deviation. So when you add those up, you get a chi-square of 0.38. Now I can tell you if the chi-square is less than 1, you are definitely not going to reject any null hypothesis ever. That's not statistically significant ever. But let's run it through anyway. So the critical chi-square is 5.99. Oh, sorry, I guess I did alpha 0.05 again. The observed chi-square for 2 degrees of freedom is 0.38. That's a lot lower than chi-square, than 5.99. Observed is less than expected. Observed is less than critical. The observed value is less than the critical value by quite a lot. Therefore, p is greater than 0.05. We don't know exactly what p is, and we don't care. And we are going to fail to reject the null hypothesis. So in conclusion, the observed distribution does not seem different from the predicted distribution. So we accept for now the hypothesis that her theory about the gene not being dominant nor recessive is correct. The next step, we don't do anything. If the omnibus test was not significant, then you stop. You might be tempted to go do 2-group comparisons because you're like, oh, no, wait, but the pink ones were different and the other ones were different. But no, you don't. You just stop. And you don't do any 2-group comparisons, even if you suspect there might be important differences, because that's one way we prevent ourselves from doing too many tests and therefore inflating type 1 error. If the omnibus test is not significant, you stop. So example number 3. Let's say 10 years ago the smoking habits of 40 to 50-year-old men, that's a 0 for old, were as follows. 43% smoked 0 packs per day, 17% 1 pack, etc. Only 6% smoked 4 or more packs per day, and you add that up, that's 100% total. So the number of categories, 1, 2, 3, 4, there's 5 categories. Definitely a chi-square situation, more than 2 categories, so it's not a proportion test. And they're just counting the number of people. If it's percentage of observations, that's the same as number of observations in each category. So a recent random survey gives the following numbers. 406 smoke 0, 164 folks smoke 1, etc. The survey was a total of 863 participants. So the question is, have the smoking habits changed? And let's say alpha is 0.01. We want to be really sure if we conclude that they've changed. So have these smoking habits changed? So when we've got this going on here, our null hypothesis is going to be that the smoking habits have not changed. And so think this through. Therefore, the recent survey values should be from the same population as the survey values from 10 years ago. I know it's different people, I know it was 10 years, but statistically speaking, the null hypothesis is saying that habits have not changed. Therefore, the data about habits comes from the same population because that population has not changed. Therefore, we use our 10-year-old survey values as the null hypothesis values. But those were in proportions, not in numbers, so we'll have to convert them into numbers. So the null hypothesis is the true smoking habits of this group are the same as 10 years ago. In other words, 43% don't smoke, 17, 1 pack a day, etc., etc. The alternative hypothesis is that the smoking habits are now different from what they were before. There's just a difference. We can't, with a chi-square by itself, we can't say what the difference is. We just say there's a difference. And so here's how you could graph those data. You can see that they're pretty close. The null value is here, and the expected value is here. The null value is here, the expected value is here. So for 0 packs a day, there are too many people smoking 0 packs a day compared to back in 10 years ago. And there are more people smoking only 1 pack a day. There are fewer people smoking 2 packs a day, fewer people smoking 3, and a lot fewer smoking 4 or more. So it looks like people just smoke fewer cigarettes in general. You could make this into a quantitative variable and just do a means test on it. What's the mean number of packs you smoke 10 years ago versus now? But they did it with this categorical ordered variable, so we're going to go with the chi-square instead. So you could add up all those yellow values. That's going to be your chi-square value. And let's look and see what that has to say. Our observed values are here. The null hypothesis says that 43% should be here, 17% should be here. So if you take 43% of 863, that's how many people should have said that they smoke 0 packs a day if the distribution was the same. Like if we had exactly the same percentages these days out of 863 people that we had 10 years ago, this is what the numbers would have been. Again, it's okay to have these decimal numbers, even though the counts are always discrete. That's fine. It helps us do more precise math. So we can look at those differences, and that's just the number version of the graph we just saw. We can look at the differences in absolute numbers here, 34.9, 17, etc. We square those differences. We divide that squared difference by expected, and our chi-squared is 20.54. Now, I'm going to tell you that that's going to be a statistically significant result, which means we reject the hypothesis that the smoking habits are the same. But consider the graph. It's not a lot different, right? So that might not have been something that you would have concluded on your own. And with alpha of 0.05 or really stringent, like 0.001 or something, you might have found some different results. But the chi-squared is telling you that those deviations are important, that those deviations add up. The chi-squared is 20.54. In other words, those deviations are a lot more than we would have expected if the new distribution had come from the same place as the old distribution, if true habits were the same. And so working through the values here, if you look up at the table, the critical chi-squared for alpha of 0.01 and 4 degrees of freedom, remember 5 categories, so 4 degrees of freedom, is 13.28. 20.54 is bigger, and therefore p is less than 0.01. We reject the null hypothesis, and the conclusion is that the observed distribution of habits is not the same as it was 10 years ago. And here the next step, if you felt like it, if it made sense, would be to do pairwise comparisons to find out where the differences really lie. Now ideally you would only do comparisons of just certain values, so you could minimize the inflation of family-wise type 1 error, so minimize the number of extra tests that you're actually doing. But you might do them all, depending on how you rationalize things. Now that's the end of our lecture today. The next one will be the chi-square independence test, and I'm sure you're looking forward to it